Large language models, LLMs, have been successfully applied to various software engineering tasks, including program repair, leveraging techniques such as few-shot learning and chain-of-thought prompting. Recently, the self-consistency approach has emerged as a promising method, which involves generating multiple explanation solution pairs for a given problem and selecting the most frequently occurring solutions. However, this approach is limited by the lack of explanations in most software datasets. This paper explores the application of self-consistency to program repair, using commit log messages as explanations. The authors find that this approach achieves state-of-the-art results on the MODIT dataset, outperforming previous prompting-based program repair methods. They also provide evidence suggesting that the correct commit messages help the LLM learn to produce better patches. The paper first introduces the concept of LLMs and their applications in software engineering, highlighting their ability to generate sequences of tokens based on a given prompt. It then discusses the few-shot learning and chain-of-thought approaches, which involve providing examples or reasons connecting input and output pairs to guide the LLM's generation. The self-consistency approach is presented as a more effective method, which involves sampling multiple explanation solution pairs and selecting the most frequent solutions. The authors illustrate the steps followed for few-shot, chain-of-thought, and self-consistency approaches in program repair, using an example of a buggy function, commit messages, and fixed function. They demonstrate how the self-consistency approach can be applied to program repair, using commit log messages as the reasoning path. The paper also discusses related work, including few-shot learning, chain-of-thought, and self-consistency. It highlights the effectiveness of these approaches in various software engineering tasks, such as code summarization, code repair, and assertion generation. The authors also mention that the self-consistency approach can be used to leverage abundant data in software engineering tasks, even when labeled data is limited. Overall, this paper presents a novel application of self-consistency to program repair, leveraging commit log messages as explanations. The results suggest that this approach can achieve state-of-the-art performance, and the authors provide insights into the effectiveness of this method in software engineering tasks. In this study, the authors explore the application of self-consistency, SC, for program repair tasks, utilizing commit log messages as reasoning paths within few-shot examples. They use the MODIT dataset and the code DaVinci 002 model, which has 175 billion parameters and demonstrates exceptional performance in code-related tasks. The research questions, RQs, focus on whether SC improves program repair performance, how many samples are needed for SC, and the impact of using random commit messages instead of original ones. The results show that SC improves over greedy decoding by 42.10% and 38.39% for B2Fs and B2FM datasets, respectively, when using BM25 to select few-shots. However, the gains are lower when using BM25, with improvements of 9.65% and 13.08%. A McNamara test reveals that the improvements from SC are statistically significant, p less than 0.01. Regarding the number of samples needed for SC, the performance consistently improves for the first 10 samples for both datasets, but the benefits taper off after this point. For B2Fs, the performance continues to improve with an increasing number of samples, although the benefits decrease. The authors choose 30 samples as the optimal number for their results, with the complete processing taking less than 5 seconds per sample. The authors also investigate the use of random commit messages instead of original ones in the few-shot samples. They find lower improvement of 3.44% and 4.18% over the baseline approach, and statistical significance was not achieved. Using the original commit messages resulted in statistically significant improvement, suggesting that the LLM is learning better reasoning paths from the original commit messages for the task of program repair. The discussion section highlights that the performance of the proposed approach surpasses that of the NatGen model, which scored an accuracy of 23.43% and 14.93% on B2Fs and B2FM, respectively. The authors note that their performance was not measured on the full test set but rather on a sample. However, since they randomly chose a large sample for their experiments, the findings are robust. They also acknowledge that commit messages in MODIT are sometimes uninformative and limited to bug-fixed, and speculate that with better quality commit messages, the model's performance with COT and SC could potentially improve. This research paper explores the concept of leveraging large language models for automated program repair. It begins by referencing several studies on language models and their capabilities in learning and generating code. The authors cite works such as Wang et al. 2022, Brown et al. 2020, Wei et al. 2022, Chen et al. 2021, and Ahmed et al. 2022, highlighting the potential of these models in understanding and generating code. The paper then delves into the use of these models for program repair, referencing various benchmarks and datasets like Defects4j, Just et al. 2014, Quixbugs, Lin et al. 2017, and Code Glue, Liu et al. 2022. These benchmarks provide a foundation for evaluating the effectiveness of language models in fixing coding errors. The authors also discuss different techniques used in program repair, including the work of Barabi et al. 2021, Zhang et al. 2021, Letellier et al. 2020, and Yi et al. 2022. These studies demonstrate the effectiveness of neural machine translation models in repairing programs. Moreover, the paper emphasizes the importance of multimodal learning, which combines natural language and source code. It cites studies such as Chowdhury et al. 2022, Xu et al. 2022, and Zhang et al. 2022, showcasing how multimodal learning can enhance the capabilities of language models in understanding and generating code. Finally, the paper touches upon the evaluation methods used to assess the performance of language models in program repair. It mentions the McNamara test, McNamara, 1947, and its application in determining the statistical significance of differences in repair accuracy between different models. Overall, this research paper provides a comprehensive overview of the current state of large language models in automated program repair, emphasizing their potential, challenges, and future directions.